With these definitions and notations, we are ready to give the statement of the theorem on the characterization of the irreducible complex linear representations of SL2C. The statement is as follows. For each integer n greater or equal to 0, there exists absolute equivalence, a unique irreducible complex linear representation pi of little SL2C on a complex vector space V of dimension n plus 1. Moreover, in V, there's a basis. Remember, this V is of dimension n plus 1. So there will be n plus 1 linear independent vectors with 0 through Vn, such that with this basis, we can explicitly write down what this complex linear representation is. And of course, that is up to equivalence. Now, keep in mind our notations above, H, E, and F, which span SL2C. So, in terms of those basis vectors, pi of H applied to V sub I will be n minus 2i times Vi for an I from 0 to n. This relation tells us the eigenvalues of pi of H are n minus 2 all the way to negative n minus 2, negative n. The second relation is, if you first apply pi to E, and the action of this linear transformation on V sub I is I times n plus 1 minus I V sub I minus 1 for any I greater or equal to 0, less than or equal to n. With the convention that V sub negative 1 is 0. And this tells us pi of E gives a backward recursive relation on V sub i's. The third relation is that pi of F applied to V sub I is equal to just V sub I plus 1 for any I from 0 to n, with the convention that V sub n plus 1 is 0. This tells us that pi of F gives a forward recursive relation on V sub i's. This is the whole statement for this theorem on the characterization of irreducible complex linear representations of SL2C. I use the label 1.66 because this is the exact same theorem in Knapp's book, so that it will be easier for you to look it up. Let me give you an immediate corollary to this theorem to illustrate its power. This is the corollary, which says any one-dimensional representation of little SL2C is 0. And the proof is quite easy. First of all, any one-dimensional representation of SL2C must be irreducible. That is because, just think about all possible subspaces of a one-dimensional space. There can only be two subspaces for a one-dimensional space. It will be either 0 or the whole space, because the dimension of the whole space is just 1. Now, by the theorem above, with n equal to 0, now there's only going to be one vector in the basis. We apply pi of h to this vector. By this relation on the left, pi of h applied to v0 will be n times v0, but n is 0, so this is 0. And now pi of e applied to v0 will be 0 times v negative 1, still going to be 0. And pi of f applied to v0 will be v1. But v1 is 0 by the convention, because here n is equal to 0, so v sub 1 is 0. They're all 0. And h, e, and f span SL2C. This tells you that pi must be 0. Namely, this representation is 0.